destination. So that helps us to route the packet around the faults really better. Negative first algorithm is still functioning really well. But what is interesting in this one is if you see XY algorithm, despite of its simplicity, despite of the fact that it's really, really simple, it's not fault tolerant algorithm, but it's still functioning really well. That's not a bad performance for a very, very simple algorithm.
So here, what is the definition of fault rate, and what is the definition of arrival rate?
Fault rate is how many faults how many faults do we have along the path? So 20%. What I mean by 20% fault rate means like 20% of the paths that we have on the network are faulty.
And not the 20% of the nodes.
No.
I see.
And the arrival rate is, I sent 3,000 packets. How many of them made it to the destination? Or how many packets total made it between the source and
so
destination?
these 3,000 packets were generated by different nodes?
Yes.
Randomly?
Random. So just to conclude this, as we can see, XY, even though it still is a very simple, but still has a good arrival rate, under 20% fault rate. For energy consumption, it's very obvious that the worst algorithm that we have here is the 8 random walk, and because we're generating a lot of packets and injecting them to the network. So this means that every time you have when you generate packets, that's energy that you're consuming. But again, if you take a look at here, XY algorithm is still functioning well under energy consumption because it always takes the minimum path. It does not make any detour between. It always goes really straight and minimum path to destination. And it has a good arrival rate, which helps minimizing resending packets, which means less energy consumption. And finally, for our latency analysis, it is safe to say that any function that has a good arrival rate should have a good latency because you're sending the packet only once from the source and destination. And for the XY algorithm, again, it has another advantage because it's always provided us with the minimum path. Negative first algorithm always provide us, also can provide us with the minimum path, minimum or non-minimum, depending on where's the location of the source to the destination to the source. And then as we can see here, all random walk algorithms have higher latency because it doesn't take a minimum path. We always take a detour. And so that's why it has higher latencies than the other schemes. To conclude the work here, as we said, as technology scales, reliability of any circuits becomes a really significant concern. Of course, implementing the current fault tolerance techniques is infeasible to implement them in a network on chip. The reason why, if you notice that I mentioned the XY algorithm and I focused on XY algorithm in my results, because XY algorithm is really easy, but it always gives us a good results, which tells us that within the current schemes that we have, while we design network on chip, the error rate is not really high. The amount of errors that are being generated are not really high, which means if we use a good error detection codes and schemes, we can contain those errors and not worry about having any fault tolerance in our routing schemes. As we notice, any deterministic routing algorithm is really easy to implement. And random walk algorithm, as we have noticed also, there's a lot of communication overhead. And if we peek into the future, and for the future work, if I want to extend this work, I would be really interested in identifying a realistic workload distribution, applying a real work data, a real work applications loads, and see how these algorithm functions. And also, I would like to implement this network on chip with virtual channels. And virtual channels usually modify and the blocking conditions that we have on any router. So implementing those schemes with the virtual channels will be, I think, will be really interesting work. Any questions?
Questions?
When you say n random walk, like 1 random walk, 2 random walk, what does that mean? Does that mean that you're sending out 8 copies of a single packet to do a random path, or does that mean that you have 8 random paths that a single packet can take?
You don't have an 8 random paths, but see, when we said we calculate the probabilities for each, and then we use a multiplicative factor, that multiplicative factor, what is the biggest value for that multiplicative factor? Would it be 1? Would it be 4? Would it be, say, 8 and thus? And when you increase the multiplicative factor, you increase the probability for that outgoing channel.
Okay.
That's what I mean by that.
And if you go back to the results, one more.
One more?
Yeah, one more. So for the XY, so it just has one path in it. If you have like a source and destination, it calculates that it will calculate only one path.
Yes.
So if there's a node in there that's failed, I mean if that's a fail, so at failure rate 20, so does that mean at failure rate, I mean, so what was failure rate again? It was
The failure rate that we had is 20% of the paths that we have between the source and destination are faulty. And I think I see your question, you're saying, yes, there's 20% and you have only one path and you're still having a good arrival rate, correct?
right, yeah.
This comes from design of a network chip. You know, what I mean by faulty is not only that, you know, how the way that we understand it in the traditional way that the router is broken and we're done. A faulty could be, it's just a congested router. And for congestion, there's a lot of scheduling techniques that designers of network on chip uses. For example, some of the techniques, even if you have a congested router, even if your packet came last, but some of the techniques looks at the destination to your source and destination. They say you have taken a long path. Your source is very fast from your destination. That means that you're taking a long time. So your latency is higher. So I will give you a priority to pass even though you came after, you know, certain packets. What I want to say here is that, yes, there are faults, but the scheduling techniques and, you know, the fact that, yes, the fault does not last. A lot of the problems in network on chip are transient faults. And in my work, I took a look at the permanent faults. So, you know, yes, you have only one path, but how to deal with the fault on that path, sometimes it's even better than having a fault route.
So when you say, so faults are not permanent faults, so you can still get through a node if you have a fault at a node?
Realistically speaking, in real implementations of networking chip, most of the faults are transient, so you still can go through the problem.
Oh, okay, so you're assuming that this is, so when you say 15%, that means in 15% of the fault, at a given time,
Yes.
you have, you cannot go through the path. And then is it, so, and is it retried?
Yes. The fact that it's a network, you always retry to send the packet.
I see.
Any other questions?
Did you compare your findings with other studies, like results?
No. This is only what I have found. This an implementation of an existing techniques. I think, you know, a comparison will be worth it because the injection rates that I have used here are really high. For the current techniques or the current literature that we have, usually the fault rate or the injection rate are usually very low.
Okay, more questions? So we will have the other two presentations next time. And incidentally, I'm going